Hello and welcome in. We are starting a new chapter here on Equilibria. In this chapter, we'll discuss a few other classes of equilibria, including solubility and complex ion formation. All right, welcome in here. Our first topic that we will be considering is solubility. In the past, we maybe have seen solubility. This is the maximum amount of a substance that's able to dissolve. We can have this in grams per 100 grams of our solvent. We could have this in moles per liter of our solvent. This solubility, it depends on our temperature. For solids dissolving into liquids, the solubility increases at higher temperatures. And we can say that intuitively, our relative solubility depends on the intermolecular forces between our solutes and our solvents. We need to break apart those solute compounds into those constituent ions by forming better interactions with our solvent. The general rule of thumb, like dissolves like. And if we like, we can have this chart of solubility rules to give us a little bit of intuition, what we expect to dissolve, what we expect to be insoluble. Now that we have equilibrium tools and strategies, we can look at this in a little bit more detail. As it turns out, this dissolving process is an equilibrium process. We can describe it using those same tools we have from other equilibria processes. We can write our K expression. Now we have a new K, we call this KSP. It is just an equilibrium constant in terms of concentrations, but now it's for the reaction of an ionic compound dissolving into its constituent ions. We do our same strategy as before, products divided by reactants. And so in our example, we can see that our KSP has the form calcium ions times our fluoride ions squared because of the coefficients in our balanced reaction, because of the phases in our balanced reaction. Solids and liquids we omit from our KSP. Some interesting intuition we can gain from this already. Our solubility depends on the value of this KSP. Things that we consider completely soluble are going to have KSP values that are extremely large. Things that we consider to be insoluble are going to have KSP values that are very, very small. As we saw before, our solubility depends on the temperature. We can use our Van Hoft equation to describe how that K changes at different temperatures. And we can use this to get some intuition about perhaps the thermodynamics of this process. We can illustrate this with a nice calculation example. What is the molar solubility of calcium carbonate in water at 25 degrees Celsius when we have the KSP value equal to 4.96 times 10 to the negative 9th? We can see that K here is very small. We expect this to be not very soluble at all, but we can figure out exactly how soluble using an ice table. Our strategy for solubility, we can say, let's have lots of our solid. If we have as much solid as possible, we can try to decide how much will dissolve. What we end up with in our ice table, we have some excess solid still hanging around. We don't actually care how much because it does not show up in our K expression. And we end up with equal amounts of calcium and carbonate ions. We can solve this ice table, we get our answer, and this value for X is precisely our solubility. X is how much of our solid was able to dissolve. That's exactly the definition of our solubility. We have a second practice problem here. I'll put up the answer, but see if you can figure this out and come to the same conclusion. We've mentioned the common ion effect previously in our equilibrium discussions. This is the idea that when we are reaching an equilibrium, if there is already one of our reactants or products present, our equilibrium position will be disturbed, and Le Chatelier's principle describes how we can counteract that and regain our equilibrium. We saw this with buffers. We can also see this with dissolving. This example shows the solubility of our calcium fluoride when there is already one of our ions present. Again, we can solve for our solubility assuming we have plenty of our solid, trying to decide how much of it can dissolve. But now we don't have 0 of our products. We're starting with some of this fluoride. Le Chatelier's principle says we have added some products compared to our last practice problem. And so our equilibrium position has to shift to the left. We are going to do less dissolving because we already have some of our product. If we want the actual numbers, ice table is a great strategy. We can solve our ice table. We can set up our K equation. If we want to simplify our lives here, we can assume that we have a small x. KSP is extremely small, and we have that common ion effect making x even smaller. So yeah, reasonable to assume that x is going to be small. We can always double check later. Our solubility when there's already some fluoride in our solution, 1.46 times 10 to the negative 12. Recall from that practice problem on the previous slides, in pure water without any fluoride to start with, we had a solubility of 3.32 times 10 to the negative 4. Our solubility has changed by orders of magnitude because we have some of that fluoride present just to begin with. This is that common ion effect in action. Our dissolving process is going to depend on the temperature based on that Van Hoff equation. It's also going to depend on the pH. When we have salts, these salts can be either acidic or basic, as we've seen. In the presence of acid or base, we can disturb our equilibrium and change how much of our solid will be able to dissolve. If we just care about this qualitatively, we can use Le Chatelier's principle. Here's an example. Magnesium hydroxide can dissolve to produce some magnesium and some hydroxide. If we add some hydroxide, that would be adding some product. Based on Le Chatelier's principle, we'd have to shift left. Alternatively, if we add some H+, and hydroxide will neutralize to form water. This would be like removing some of our hydroxide, and to counteract that, our system would have to shift right. This is one specific example, but notice here, our magnesium hydroxide is some kind of basic salt. Our basic salts will dissolve more in the presence of acid. Our basic salts will dissolve less in the presence of base. A couple of practice questions here. Magnesium hydroxide in acid or neutral solutions, what can happen? Well, we saw in acid, we are going to remove some of our product and we'll have to shift right. This will increase the solubility, and therefore magnesium hydroxide will be more soluble in acids. Magnesium fluoride. Is this going to be more soluble in basic solutions or neutral solutions? Well, let's write out the reaction. If we add base, can we react with anything? If we imagine this beaker, we have a big pile of solid, we have a little bit of magnesium, a little bit of fluoride, and we've added some hydroxide. That hydroxide can react with our magnesium. It's not going to react with fluoride. Right? Hydroxide and fluoride are both bases, both negative, but maybe we could have this reaction with magnesium. This is a precipitation reaction. It's the reverse of our dissolving reaction. And we saw actually that magnesium hydroxide is not very soluble. It will like to form precipitates. What we can say then is that when we add hydroxide, this will react with our magnesium. This will cause our magnesium to form a precipitate and be pulled out of our first equilibrium. This is a disturbance to our magnesium fluoride dissolving KSP equilibrium. And so in the presence of base, we're removing product, we'll have to shift forward. In the presence of base, our magnesium fluoride will be more soluble because it's turning into magnesium hydroxide. To help us out here, we can try to write out the reactions that are happening. We can try to draw a picture describing what is in our beaker. We can try to identify all possible reactions that might occur. Then use Le Chatelier's principle to draw some conclusions. Let's see if we can try a couple more examples. For C, benzoic acid is an acid. We can write that acid equation. When we add acid to this solution, this would be like adding a product. Le Chatelier's principle tells us we'd have to counteract that and shift left. In the presence of acid, benzoic acid will dissolve less. In a neutral solution, we can dissolve a little bit more. For D, calcium carbonate dissolves into calcium ions and carbonate ions. If we add acid, acid doesn't show up in our reaction that we've written so far, but it can react with one of those products. Carbonate here is a weak base. When we have acidic solutions, we are going to be removing some of these products, and we'd have to shift over to the right to remake them. Based on Le Chatelier's principle, that first reaction will occur more in the presence of acid. This is similar to what we saw on that first example. When you have something that dissolves into a weak base, right? We have a basic salt. That dissolving process happens more in the presence of acids. We can leave the last two as practice here. Convince yourself that the answers should be this, based on Le Chatelier's principle, based on the reactions that can occur. We've been talking about the dissolving process. We can also flip this on its head and think about precipitation instead. Precipitation is the process of forming a solid from dissolved species. Our KSP value tells us how much we'll be able to dissolve. We can also use it to decide when a precipitate will show up. If we have a concentration of ions in our test tube that exceeds our KSP value, that means our ions will not be at equilibrium and will form that precipitate. We can look at this as an example. If you had cadmium sulfide dissolving into cadmiums and sulfides, this process is described as KSP, this dissolving reaction. If we have some amount of ions and we want to know if that reverse process will occur, well, the reverse process of this occurs when our Q value is too big. We can calculate the Q value if we know these concentrations. If it's larger than our KSP value, then our precipitate will form, which we can see up on these images. These cloudy, murky solutions are going to be our precipitates. Here's a calculation for us. Will a precipitate form when we have 1 ml of 0.05 molar sodium hydroxide and 1 ml of 0.085 molar aluminum chloride? We know the KSP value for aluminum hydroxide is extremely small. Are the concentrations here going to be high enough to form that precipitate? Step 1, we can write out our reaction corresponding to KSP, aluminum hydroxide forming aluminum and hydroxide ions. Step 2, we can figure out our concentrations. Since we mixed two test tubes together, our volume has doubled and our concentration has halved. And now that we have our concentrations and our equation, we can solve for Q. Our metric to decide if our precipitation reaction will occur, we want to be doing the reverse of the reaction we wrote, which means we need to have our Q for this process be larger than our K for this process. In this case, yes, our K is extremely, extremely small, and our Q is going to be much bigger, and so we will see a precipitate. There we go, a nice throwback to some strategies that we've seen in the past, but now talking specifically about dissolving and precipitating. A nice laboratory technique we can introduce here, we can selectively precipitate certain ions in our solution based on their relative KSP values. If we have a mixture of ions in our solution and we slowly add some kind of precipitating counter ion, we will only start to see precipitates when the Q value for our dissolving reaction is larger than our KSP for our dissolving reaction. This might occur at different concentrations for our mixture of ions. What this means is we can slowly add some other solution to our mixture and have only one of our cations start to precipitate, or vice versa, only one of our anions start to precipitate. Let's look at this quantitatively first. If we have 0.022 molar of iron 2, 0.014 molar of magnesium, we can figure out what amount of carbonate is necessary to precipitate each of these. We get to see a precipitate when our Q is bigger than KSP. Well, we can try to decide the point when Q is exactly equal to KSP, and that is going to be the cutoff when our precipitate exactly starts to form. Our amount of carbonate is going to be equal to 1.4 times 10 to the negative 9th molar. This is the amount of carbonate that needs to be added for our Q to be exactly equal to our KSP. Any tiny amount more than that, and a precipitate will start to show up. We can do a similar analysis for our magnesium. Carbonate can be added until its concentration is 4.34 times 10 to the negative 4th molar. Anything more than that, and our magnesium carbonate will start to precipitate. The smaller our KSP value, in general, the easier it is to precipitate. This also depends on the concentrations of our starting materials. Notice we're starting with more of our iron and less of our magnesium, and so that will affect our calculations as well. But with those two things taken into account, we can decide exactly the amount of carbonate needed to form each of these precipitates. The smaller amount of carbonate that's required will lead to our precipitate showing up first. So iron to carbonate will precipitate first. As soon as we have 4.34 times 10 to the negative 4th molar amount of carbonate, then we can start to see both precipitates. That's why we want to add this carbonate slowly, so we precipitate only one, right? Selective precipitation, before precipitating out both. We can remove all the iron, and then maybe we can remove our magnesium. A nice way to separate and perhaps purify some of our materials. We can use this technique qualitatively as well. Instead of dealing with all these calculations, we can design our experiment to separate and identify our various species. Here is a scheme utilizing these phenomena. We can start with a whole mixture of cations and separate them based on the way that they selectively precipitate. If we have all of these metals, only some of them will precipitate with chloride. The rest will remain in our solution. If you add H2S, some of them will precipitate with sulfides. Others will remain dissolved. If you add hydroxide, some of them will precipitate at pH of 8. Others will remain dissolved. If we add some phosphates, we can get some insoluble phosphates, whereas other cations might still remain dissolved. So many ways of doing this. We can set up a schematic for separating and identifying and purifying some of these various cations, or alternatively, some of our various anions. We want to get back to a quantitative question quickly here at the end. We can also figure out these values numerically using our equilibrium and ice strategies. If we are mixing solutions together, well, a lot of this equilibrium math is deciding what is the easiest way to attack these problems. When we're mixing chemicals together, we can assume that we have a complete reaction first, do stoichiometry, do a limiting reactant style question, and then afterwards we can try to consider equilibrium that might show up. Right? This might make our question as easy as possible. If we have 2 mils of our 0.05 molar silver nitrate, 2 mils of our 0.1 molar calcium chloride, what do we have when we reach our equilibrium? KSP for silver chloride is extremely small. We're going to have mostly our silver chloride precipitating. After that, we might have some of our silver chloride dissolve just a small amount. Let's break it up into those two steps. We're starting with none of our silver chloride, and we have 0.1 millimoles of silver nitrate, 0.2 millimoles of calcium chloride, which corresponds to 0.4 millimoles of our chloride. If we want to build as much of our silver chloride as possible, silver is going to be our limiting reactant. And so let's use that up completely as we go back to the left here. This is our stoichiometry step. We end up with 0.3 millimoles of our chlorides and some amount of silver chloride as our precipitate. Now we want to attack this in terms of equilibrium. We can do our ice table. We have some of our solid, we have none of this silver ions, we have, some molarity of our chloride, and we're going to create a little bit more product. X here is going to be extremely small. We have an extremely small KSP, and so we can set up our K expression using that small x approximation. And we can find some value for X. Our amount of silver in our solution will be 2.13 times 10 to the negative 9th molar, and our amount of chloride will be about 0.3 over 4 molar, 0.075. Right? Like we said, this technique, just trying to make the math as easy as possible. Can we try to do as much of the reaction as we possibly can, and then inch back towards equilibrium a little bit? This allows us to utilize the small x approximation and makes our calculations much more straightforward. One last problem here, we can leave it as practice. I'll put up the answer in just a moment. That's what we've got for this video. Thanks for being here. Thanks for hanging out. Let me know if you have any questions, and I'll see you in the next one.